I feel like this video is already long enough, so I might have to split this into a two-part video. In any case, for the next part where I'm testing the power supply, I will just be showing you the results without getting into too much detail. Front panel voltmeter accuracy was checked with my HP 3441A 6.5 digit multimeter. I grabbed a bunch of measurements and compared them with the ones reported by the power supply front panel with no load attached. The claimed specs were not great to start with, plus or minus 0.3% plus 3 digits, so the power supply easily met these, staying within 2 counts for the entire range. I also tried the measurement under a load of 2 amps and 4 amps, and once again there were no significant changes and the power supply met the specs. There is no remote sense capability on this unit, but they are sensing the output voltage correctly right at the output terminals. This video is sponsored by jlcpcb.com, a professional PCB supplier who can offer 24 hours turnaround time for prototype PCBs for just $2. You also have a selection of solder mask colors with no extra cost and affordable laser cut stencils, so it's definitely worth checking them out. Next, I checked the current meter accuracy, and once again the specs are not great to start with, plus or minus 0.5% plus 5 digits, and they say digits, but this should really be called counts. In practice, the results are really good. I started by taking a bunch of measurements in the lower range under 100 mA, then with 100 mA increments, and then larger increments as it went up the range. To my surprise, there was no observable error at the given resolution, not even with measurements under 100 mA, which is impressive considering the cost of this unit. Next, I'm going to measure the voltage ripple. The spec is given at 100 mV peak-to-peak typical, which is not particularly good but acceptable for a switch mode power supply. I added some filtering to the output of my AC transformer to ensure the lowest possible noise. I have a 4700 microfarad capacitor, a 1 microfarad and a 0.1 microfarad capacitor, and an additional common mode choke. First, let's check the noise at the output of my transformer with the Riden power supply disconnected. And as expected, the noise is really low, about 3 mV peak to peak, and about the same RMS noise. I'm probing this right at the output of the filter stage with a low inductance ground connection. This will of course be a different situation if you are using the recommended switch mode power supply they offer. That unit will spill out far more noise than my transformer, and some of that noise will end up at the output of the power supply. But watch what happens after I connect the RD6006 power supply to my transformer. There is no load attached, the output is turned off. I am measuring on the same point at the output of my filter stage, which is now connected with the input of the power supply, and the noise went through the roof. I am seeing above 200 mV peak to peak and about 50 mV RMS. And all of this is injected by the power supply, which is not ideal at all. But let's see what kind of noise we get at the output of the power supply with no load. And we get around 40 mV peak to peak. That's already an improvement. This is the noise at 0.5 amps, about 45 mV peak to peak and 17 mV RMS. This is at 1 amp, 1.5 amps, 2 amps, 2.5 amps, 3 amps, 3.5 amps, 4 amps, and 4.5 amps. We have about 75 mV peak to peak and 26 mV RMS noise. This was measured with the output set for 5 volts. These results are not bad for a buck converter, and it's certainly meeting the specified ratings. Next, let's check if there is any voltage overshoot in some special situations, because this is where these power supplies often have surprises. First, with no load, the power supply is set for 10 volts. Let's turn it on, and I have 3 scenarios here. First, the power supply was running and I just switched the output on. Second, the power supply was in standby and I turned it on using the soft switch. And third, the power supply was unplugged, which is the equivalent of a hard switch present on the case, and I plugged it in with the output set to turn on at power up. For the first two, the power supply is already running and regulating, so the waveform looks good, there's no overshoot, it's just a bit slow to get to 10 volts. But the third test with the hard switch shows some problems with the power supply. We have some negative spikes. The output first goes up to around 6 volts, then goes back to 0, then rises again to the set output. This kind of behavior is dangerous in a bench power supply because it might fry sensitive electronics left connected to the output of the power supply. Now I'm going to repeat these tests, but this time with a load connected to the output. A 4 ohm resistor, which at 10 volts means a current of 2.5 amps. Once again, the first two graphs looks okay. These are with soft switches, but the third one with the hard switch presents some problems. We got some negative spikes, then the voltage jumps up to 5 volts, then back down to 0. Then after about 800 milliseconds, it starts rising to the set voltage. This kind of behavior might, for example, cause a particular circuit to lock up. It's also a good idea to check for voltage overshoot while in constant current mode. The power supply is set for a limit of 0.5 amps, but we know our resistor is going to draw 2.5 amps, so it's going to work in constant current mode once it's turned on. Once again, the first two graphs look okay with the soft switches, but the third one with the hard switch still has that spike present roughly 800 milliseconds before the actual ramp up of the power supply. Now let's check if there is any current overshoot. We can imagine having the power supply set for a certain current limit. We forget about the circuit connected to the output and we turn on the power supply. Will it limit to the set current, or will there be a current overshoot for a brief moment? For this measurement, I'll be using my joule scope. It's a perfect tool for this job, and you can watch Voltlog 211 for a review of this tool. So the output from my power supply goes through the joule scope, and onto the output of the joule scope I have my load, which is the same 4 ohm resistor I've used previously. First we try the soft switches on the front panel. The current is limited to 500 milliamps as configured, but our 4 ohm resistor is going to try to pull 2.5 amps. There is no overshoot here, the waveform looks clean. So next we try the hard switch, and once again we have no overshoot. Another scenario is when you suddenly connect a load on the output of a power supply set to constant current mode. A current overshoot is to be expected in this case because of the capacitors placed on the output of the power supply. Even if the power supply regulation kicks in, you still have energy stored in the output capacitors. That energy is going to discharge into your load, and depending on the amount of capacitors the power supply has on the output, this overshoot will be higher or lower. In this case, we know the power supply has a lot of capacitance on the output, so I'm going to expect an overshoot. Let's check the waveform. The power supply was set to limit at 0.5 amps, but we can see the overshoot reached 2.2 amps, and it took about 4.5 milliseconds to get back to 0.5 amps. Unfortunately, this issue cannot be fixed as long as we have those big capacitors on the output, and they kind of need those capacitors to keep the noise down. Next, I will take a look at the PC connectivity and Wi-Fi capability of this power supply. Even though it has a Wi-Fi module based on the ESP8266, the manufacturer recommends you to connect to the PC via USB. They claim the connection through Wi-Fi with the PC is unstable. So I connected via USB, I downloaded and ran the software they provide, which is like a portable app, no setup required. The power supply appears as a virtual COM port, so you just have to connect to that port and then you are able to access all of the functionality. One downside here is that after connecting to the PC you lose front panel access because the app automatically locks the front panel. I wish this was an option which you could disable, because sometimes you might want to still operate the power supply from the front panel while doing some data logging, for example. The app window does not scale, it's either a smaller format or it's maximized to full screen, but in this window you get pretty much all the info you need as well as the controls. Right-clicking on the graph gives you the option of exporting that as an image or CSV file, and using the scroll wheel on your mouse you can zoom in or out. On this main tab you also have the battery charging panel as well as the option to calibrate the power supply, and you'll find instructions on how to do that in the user manual, but mine was already well calibrated from the factory. Going into the advanced functions tab you get the option of programming the power supply with set voltage and current with numerous steps and delays, and this can be useful if you are doing some product testing. Next we have a tab for firmware update, but I'm already running the latest version, and it also gives you the option to set your own startup image to pimp your power supply, which of course I did immediately after carefully reading the warning they give me. Moving on to the mobile app, for some reason I wasn't able to connect from an iPhone. The connection was always stuck at this step, connecting to Wi-Fi, but I did manage to connect with an Android phone, and the app itself is okay for monitoring a few parameters and maybe turning the output on or off, but nothing more. Although you can do it, it's not friendly at all to set voltage or current with that knob on a touchscreen. This would have worked better with buttons. So in the end, I don't think I'll be using the mobile app as it is. The PC software is much more friendly and usable. And now, as a summary, I'm going to tell you what I think about this power supply, and I'm going to compare it with the Gophert NPS-1601. Now, one advantage of the Gophert power supply is the ability to connect multiple units in series or parallel to increase the output capability, while Riden advises not to do this with their power supplies. I'm not sure why, because in theory it's an isolated power supply, but this is how they responded on a forum when a user asked about this capability. The Gophert power supply also has less noise on the output, no voltage overshoot, and minimal current overshoot due to smaller output capacitance. The Riden power supply has quite a large current overshoot and presented some unwanted spikes when the power supply was turned on using the hard switch. Another advantage of the Gophert power supply is how compact it is. It doesn't have any fans and it's completely passive cooled, zero noise added to your lab. The RD6006, when it's built completely into the enclosure, has a total of 3 fans with at least one of them running continuously. The fan on the front panel itself will start to run automatically after you go over 40 volts on the output. However, the Riden power supply also features some nice advantages over the Gophert power supply. It has a nice color TFT display which can show a lot more info. It has PC connectivity with fully featured app. You can control the power supply remotely and do data logging that way. It has better accuracy for current and voltage measurements. And the RD6006 has an easier to use front panel with a keyboard for easy adjustments, and in general it has more features than the Gophert. But let's not forget that if you get the full package for the RD6006 plus the metal enclosure plus the switch mode power supply, you end up paying more than twice the cost of the Gophert NPS-1601. So it's up to you to decide if those extra features of the RD6006 are worth the extra money. But I can tell you this, it's a nice power supply. I like it, and it's certainly good enough for most hobby projects. As usual, you'll find links for the products shown in this video in the description below. Thank you for watching this rather lengthy video, and I'll see you next time with a new one.